Hi and welcome back. So, sorry about the episode in the last video, just a little bit crazy. Anyway, I've got the summing formula here, which is what we're going to talk about now. What if we want to sum a geometric sequence? So we might have a geometric sequence like this one, which I've used a few times because it's nice and simple. 2, 6, 18, 54. What if I want to calculate the sum of this sequence for, say, I don't know, the first 6 terms? Well, I'm going to tell you this is the formula, and if you hold on, towards the end of the video I'm going to show you where this formula comes from. But for some of you might just want to see it used and then move on. Now, really in these videos I'm not going to do the hard problems. You might be given the sum and asked to find R or something else, so you just got to be careful and be thoughtful about what you might be asked. So sum n is equal to this, and I'm going to do it for that. You'll notice here sum of the first n terms. We know n because I've asked for S6. We know term 1, and we know R, and that's all we need. So I'm going to start by just summarising what we have and need. T1 is equal to 2, R is equal to 3, and N is equal to 6, and we can use that to find S6, which is going to be equal to 2, T1, times by 3 to the power of 6 minus 1 over 3 minus 1. So 3 to the power of 6 minus 1, I won't throw my calculator this time, but let's have a quick look. It's going to be a pretty large number, it usually is. 3 to the power of 6 minus 1 is 728. So I get this. It's equal to 2 times 728 over 2, which equals 728. That's nice and easy. That's the sum of the first 6 terms. Is it reasonable? Sometimes you might be asked to evaluate the reasonableness. If I have a look at my original data set, the next term times 3 is 162. And the next term, times 3, is going to be 486, I believe. Check me on that. But if I'm adding those together, yeah, 728 is about where I expect it to be. So I'm confident in this formula. So in a moment I'm going to show you where this formula comes from. Okay, so without exception, formulas always come from generalising. And that means we take the numerical example we've just had, and we change it and just do it algebraically. So algebraically it would look like this. The sum, well actually we won't do the sum, T1, T1R, T1R squared, T1R cubed, so on and so forth. So of course the sum n, which we're trying to calculate, now we'll do the sum, is equal to T1 plus T2 plus T3 plus plus Tn, which can be better written as T1 plus T1R plus T1R squared plus plus T1R to the power of n minus 1. Now we could take this sum n, this is the tricky bit, and you've seen sometimes I go, let's just do this, and you go, why did he do that? Makes sense, but this is from somebody much smarter than me who's come up with a way of doing this. So what I'm going to do is I'm going to multiply the whole thing, everything, by R. That's okay, it's an equation. I can multiply everything by R with the same thing. So I get R times the sum of n is equal to, and I'm just going to slide it across, you'll see why in a minute. T1R, because that term 1 times R is that. Term 1R times R is term 1R squared. There's lots of stuff in there. This previous term times R will be term, that'll be the previous term will be term 1R to the power of n minus 2. Times R to the power of n minus 1, plus term 1 R to the power of n. So this times R will be that. Pause the video now and do a little bit of maths if you're not convinced. Okay, now just imagine for a second if I did a little subtraction. So I'm going to take this top line and I'm going to subtract the bottom one. So over here it gives me Sn minus R Sn, and over here it gives me T1, but T1R times minus T1R disappears. And T1R squared minus T1R squared, again, they cancel each other out. And all this stuff here minus all this stuff here, well, that's matching terms all the way up to n minus 2. And even this is a matching term, but I am left with this guy. So I've got minus T1R to the power of n. So now I've done that subtraction, I'm going to factorise Sn out. I get Sn, 1 minus R, equals T1. I'm going to factorise T1 out, 1 minus R to the power of n. I'm going to divide through. Sn equals T1, 1 minus R to the power of n, over 1 minus r. But hold on, hold your horses. I know. 1 minus r to the n, and I've got r to the n minus 1. That's not the same formula. Well, it actually turns out here that if I take this and I multiply the top and the bottom by -1, it gives me this. The term 1 stays the same, but I can invert the other two. I get r to the power of n minus 1 over r minus 1. It also turned out that if instead of subtracting this line from that one, I did it the other way around, I'd get this formula here. But what's important is it's good that you know there's two variations. One of them will be on your formula sheet, but you can use the other one. If you want to avoid negatives, which is commonly a nice thing to do, if r is greater than 1, go with this guy. If r is less than 1, go with that guy, and you'll avoid negatives. Anyway, there's the sum of a geometric sequence. All the best.